So in today's class, I will cover the third subtopic, which is imperfection. What do you know about imperfection? So imperfection means you did not get an ideal things that you want during the manufacturing process, right? So we have looked into several fabrication process, which involve oxidation, and then we also look into a doping process, which involve ion implantation as well as diffusion, right? And then we have looked into deposition. So there are many types or there are many techniques for deposition, but we look only into CVD and also PVD, chemical vapor deposition, and also physical vapor deposition. And then we look into the patterning process, which involve lithography, and then how the projection system looks like, and what are the parameters involved in determining the minimum feature size of the transistor that we want to fabricate or the geometry that we want to fabricate. And then lastly, we also look into removal process, which include etching for patterning. And then we also look into CMP, chemical mechanical polishing, which is used to make a planar surface. Right. So as we have seen in the last class, there are many factors that can affect the manufacturing or the fabrication or the process involved in making the chips. Okay. So for example, in oxidation, there are things to consider, for example, like temperature. So you need to control the temperature. And if let's say you bake the wafer in the oven, right, to form the silicon dioxide, where heating process is involved, all right? So the time being exposed in the oven will determine how thick your silicon dioxide, for example, will be formed on the chip, all right? And not only that, there are other parameters also that can affect the final output that we obtain in the oxidation process. So what kind of imperfection that you can observe during oxidation? Or what kind of manufacturing defects that you think you can observe during oxidation process? Can any one of you name examples? What do you think can go wrong during the oxidation process? And if it go wrong, what could happen to the oxidation layer that we want to fabricate? Can you give a try?
Okay, can I guess?
Yes, Afiq. You want to give a
Corrosion?
try?
Or
Corrosion?
erosion? Yeah.
Doctor,
Corrosion,
how about impurities? Like, I don't know, like Afik told, maybe.
impurities.
Yeah, like by the air or something.
Okay. So, yep, you can have impurities. Okay. All right. That's a good try. What else do you think can happen during the oxidation process?
Thickness, the oxide thickness maybe not as what we are planned.
Okay. Very good. So, there's a specific term. We call it surface roughness. Okay. So, as you can observe here in this picture, you can see that the surface of the oxide layer, oh, this is not oxide layer. So this is the gate. Okay. So this is the gate. But imagine this is not channel. Okay. Imagine this is oxide layer. Imagine this is an oxide layer. And above here is your gate. And below here is your channel. So you can observe actually during the oxidation process, surface roughness is one of the manufacturing imperfection that could occur during oxidation process. In the past, this surface roughness does not really make any problem. I mean, there's not much issue when we have surface roughness problem okay. Why? Because in the past, for example, if let's say TOX is maybe like 30 nanometer, for example lah, okay, 30 nanometer, and the surface roughness here is maybe T rough is maybe is around plus minus 1 nanometer, right? So 30 nanometer plus minus 1 nanometer, so the difference is not much lah, alright? So the difference is not much. But when we scale down the transistors, we also scale down the T oxide. So when we scale down the T oxide up to 2 nanometer, for example, alright, and the surface roughness is plus minus 1 nanometer. So this could vary the transistor parameters greatly, alright? So some part where you have only 1 nanometer difference, okay, so some part when you have, for example, here you have 1 nanometer, and some part here you have, for example, 2 nanometer, right? So in some part you have 2 nanometer thickness, in some part you have 1 nanometer thickness, and because of this different thickness, you will have different electrical field across the TOX, right? And this different electric field can produce variation in the amount of electron that can flow through in the channel. And hence, because of that, it will greatly affect your threshold voltage. So threshold voltage will be greatly affected by surface roughness during the oxidation process. Okay, is there any question? Faham ke?
Faham, Doktor.
Alright, great. Okay, so next, let's look at doping. So now, what I want you to think of, okay, think about what kind of imperfection can happen during the doping process. Okay, anybody would like to give a try? What kind of imperfection that could occur during doping process?
Extra dopants maybe. If like giving a lot of dopants, and there
Okay.
might be some effects. I'm not so sure.
Okay.
I'm just guessing.
All right, extra dopants. All right, at least there is a try. Anyone else would like to give a try? What kind of imperfection that could occur during a doping process?
Kan kalau doping ni kita kita introduce dopant to the substance kan. So kalau contoh kita dopant hole, mungkin kita introduce hole dekat tempat another substance. Macam tu.
Okay. Alright. Very good. Alright. So there is a specific term for that. Right. So we call this random dopant. Random dopant placement. Right. Okay. So during the doping process, okay, so we have learned two techniques. One is diffusion and another one is ion implantation. And we know by using ion implanters, we can have a very accurate doping profile because we can control the location of the dopant that we want to place, right? Either in X and Y axis as well as Z axis, how deep it can go in the substrate. In the past, we don't really care the placement of the random dopant because the substrate material is quite large. Okay, so wherever the dopant will be placed, it doesn't matter because the electron can still flow from source to drain in the channel. But as we shrink down the transistors, okay, so we increase the doping concentration. So we increase the S. The S, the scaling factor. So we increase the doping concentration in the transistor. So when we decrease the size of the transistor, so we reduce the bulk material, but we increase the number of dopants into the bulk material, right? So what will happen is that the placement of the dopant can affect the flow of the electron in the active channel. So it is very important in small scale devices, we control the position of the dopant such that it should not introduce a lot of variation to the threshold voltage. Because if let's say you have some dopants, all right, so if let's say you have one dopant very near to the surface of the silicon and silicon dioxide interface, all right, it may interrupt the flow of the channel because the channel of the electron is actually very thin under the oxide layer, right? So when you introduce the dopant, if you introduce it in the middle of the channel, right? So you will have a certain threshold voltage value. And if you place the dopant very near to the source terminal, okay, you will have another threshold voltage value. And if you place the dopant near the drain terminal, you have another threshold voltage value, right? So this is the reason why during the manufacturing process, we can observe there are parameter variation in the transistor parameters. So when we go to smaller devices, it is important to control the position of the dopant so that we will have a consistent transistor performance. So for example, we really want to have a threshold voltage of 0.2 volt. So all the transistors that we fabricate will produce 0.2 volt or maybe plus minus sikit je lah, alright? For example, we want to fabricate 0.2 volt. Suddenly, the one that we fabricate is, one is 0.05 volt and another extreme end would be like 0.5 volt, for example. So we don't want this variation or very large variation in the threshold voltage, which introduced during the doping process. Okay, is there any question? Okay, so when we go to smaller devices, so usually we opt for ion implanters lah because we want to have a very accurate doping during the doping process. All right, so now let's look into deposition. So what kind of imperfection that you can observe during the deposition? So we have CVD and PVD. If you can recall the process, what kind of imperfection that could occur during deposition process?
Irregular surface.
Okay, very good. So deposition process can also introduce irregular surface. Okay, what kind of parameters that could affect it when you have irregular surface? Okay, so for doping, it will change the threshold voltage. Okay, so threshold voltage will be varied. Okay, how about deposition process? What kind of parameters that it could affect if you have irregular surface?
Thickness problem tak?
Okay, it's a thickness problem, yes. But I'm asking what kind of parameters. For example, here we have threshold voltage. Here, threshold voltage. So for deposition, what kind of parameters that can be affected?
Is it COX?
COX. Do you want to explain further? Okay, all right. So COX. Okay, thanks, Dee. All right, so COX could also be affected lah during imperfection of deposition process when we have metal layer formation lah. All right. Okay. So so this can occur if you deposit oxide layer and you have surface roughness or irregular surface or different thickness of the deposit material, and that can introduce different or vary the COX parameter. If let's say you deposit the epitaxial layer, right? So we know epitaxial layer is introduced before we start fabricating our transistors. So that could also vary the resistivity, for example, in the epitaxial layer. So, and this could introduce different mobility constant, different mobilities for the electron to move from source to drain terminal, right? So it depends. So for deposition process, it depends on what material that you are depositing, and of course, it introduce irregular surface. So this is the main issue in the manufacturing process, imperfection. And depending on the material, then it will cause the correspondence, it will introduce parameter variation depending on the material being deposited. All right, so next, let's look into patterning, okay, lithography. So what kind of imperfection that could occur during patterning?
Not as terancang.
Okay, not as terancang. Okay, what do you call it?
Tak sama dengan kita punya design.
Okay, so you will have deformation of pattern. So for example, you want a square shape, but you have an oval shape. Or you want an L shape, but you obtain macam tu kan, alright? So if you have different pattern that is being fabricated on the wafer, alright? So it could affect, for example, if you have diffusion here, diffusion area here, and diffusion area here, right? So this one should be okay lah, because the active channel, which is here, and the one that is fabricated here, is within the spec limit lah, okay, basically. But if let's say you have a diffusion area which is larger, and then you have something, and then when you fabricate too, you have something like this, right? So if you have this kind of defects, this will greatly affect your transistor parameter. So it could affect your threshold voltage, okay, and it could affect your high on and high off. If let's say you are looking at the metal, for example, so this kind of pattern will introduce different R value, and perhaps maybe C. And this could affect the delay in the circuit. Alright. So patterning is the biggest issue lah, or the biggest concern that we need to take care, because patterning is the process that we do or we repeat many times in the fabrication process. During the patterning process, we want to transfer whatever pattern that has been designed by the circuit designer onto the surface wafer. And this pattern should work as what it has been designed by the designer. So if it doesn't work, then we need to either redo the circuits, okay, or we have to interfere or interject or introduce methods to help improve the fabrication process, right? So we have the optical proximity correction, we have phase shift mask, okay, and then we also have off-axis illumination, and there are many things that we can do in order to help the fabrication process during the patterning. Okay, so this technique is what we call reticle or resolution enhancement technique. So lastly, removal. So what kind of defects that you can observe during removal process?
Maybe removing extra of the substance that we have already done before this.
Okay, so you have over etch or under etch problem, right? Very good. So we may have over etch or under etch problem. Okay, what else that we can observe during the removal process? Again, the thickness variation, right? We can also observe thickness variation. Okay, so removal process is also another important process because it is being paired with the patterning process lah. When you pattern, you need to remove, to etch lah in order to form the pattern. Pattern lithography etching, lithography, CMP, lithography, banyak lah, okay. So they are repeated process. Okay, so based on these issues that you have observed, what kind of parameters that could affect could be affected? So how the transistors or the chip performance can vary if you have under etch or over etch or thickness variation in the removal process.
COX tu.
Okay, so we can have a COX, for example, in the metal layer formation. Okay, or maybe on the transistor as well, you can. Okay, depending lah. Okay, so, I mean, you have to explain lah. If let's say you want to you want to say that it is COX that is being varied, then you have to explain a little bit more lah. Alright, so what else could vary? The resistance as well. This is in the metal layer. You can observe some of the under etch or maybe apa tu kita panggil dishing effects. Okay, so we can observe dishing effect, and then we also can observe erosion effect. Okay, so it can vary the resistance on the metal layer lah. Okay, if you have this kind of effects. Alright.
Doctor, that means
Yes.
the time delay also is different, right?
Yes, correct. So you can also affect the delay of the circuit performance. Correct. You are right. Okay, is there any question or anything that you would like to ask? Nope. Right. So we have seen performance variation lah because of this manufacturing imperfection. Right. Okay, how about reliability? So how reliability differs from variation? So we have variation in terms of the performance. Okay, and then we also have another one is a reliability issue. What is the difference between reliability and performance variation?
Doctor, is this something related to a time delay?
Okay,
Or,
very
I
good.
mean, I'm just guessing.
Yes, it's a good guess. So it depends on the time, all right? So when you are doing final tests, for example, right? So when you observe threshold voltage variation, that is what we classify is as performance variation. T before we ship the chip to the customer. Time before we ship the chip out, right? So that is performance variation, and reliability occurs after the things has reached the customer. So after a certain time of usage, then you start to see the issue coming in, right? So what kind of reliability issue that has been highlighted in previous class? Can you recall any of it? Okay, so I think I have mentioned about electro migration. Okay, so electro migration is one of reliability issues. It happens after a certain period of time due to the high current density in the metal tracks, right? So if the metal tracks being exposed to high current density after a certain period of time, the molecules of the aluminium can change place. I mean, they can move places from one to another. So this is what we call electro migration. So it happens after a certain period of time. And because of this, it can change the resistivity of the metal track, or it can cause fatal defects. It can either introduce shorts or open circuits in your chip. Okay, so this is one of the reliability issues. All right, so imperfection could occur due to raw materials. Okay, so the materials that is being produced or is being supplied to make the transistors, or it could occur from the equipment. So this is what we call the manufacturing limit lah. Okay, so if it comes from the raw material, it could be due to impurities or it could be due to physical limits. And then also another reason why we have this kind of perfection is of course the environment. For example, during the process tu suddenly ada bergegar ke kan, so it could affect the lithography process, for example, because you have very short depth of focus. Okay, so that could be one example lah, alright. So it can introduce defects in the wafer, okay, and then during the etching we can have defects as well. During the lithography we can have defects as well, and then during the deposition we can also have defects. So all in all, alright, accuracy and precisions are very important in making the transistors, in fabricating the transistors in the manufacturing process. So this imperfection could introduce performance variation. So this is very obvious. It could introduce performance variation, and performance variation is the biggest enemy of the circuit designers, right? Because we have designed the circuit to pass a certain specs, and then suddenly you have a large performance variation that you did not control during the fabrication process, and it caused the chip to fail, right? So performance variation need to be taken care during the circuit design. So that's why after you have completed your design, we run the circuits based on worst condition and then based on best condition lah. So to the extreme. This is to cater any manufacturing variation that could occur during the fabrication process. Apart from the performance variation, we can also observe thermal issues in the chip, right? This is more towards the, for example, the transistors maybe have a larger leakage current, and this leakage current could introduce more leakage power, and this leakage power will introduce higher heat dissipation. So power is being transferred into heat. So this could introduce thermal issues. Also, if you have very high resistance metal track and you have very large current densities, so this will introduce higher I, higher R. So you have P equals to VI, so P equals to I squared R. So if you have this, then it can also introduce higher power, and this power will be transferred into heat and cause thermal issues. Not only that, you can also introduce reliability issues. Okay, so one of the problem could be due to high current density and introduce electro migration, or in some process, for example, in NBTI, negative bias temperature instability. So that is another reliability issue. So this happen during the fabrication process lah. You have nitrogen in your oxide layer to prevent the boron from penetrating the oxide. So if you have too much nitrogen, so it can induce negative bias temperature instability, and this MBTI will introduce threshold voltage variation, right? So it could introduce threshold voltage variation, and this is activated at high temperature. So if you have high temperature, so this effect could be activated. So this can cause reliability issue as well. And of course, the main important things is that if you have this kind of issues and variation, it could greatly affect the parametric yield. Okay, so what is yield?
Good output.
Okay, the pass chip lah, right? So the chip or the circuits or the transistors that pass the specification, right? So parametric yield is the good dies or the good chips. We don't want to, for example, we fabricate 1 million transistors and only 200,000 transistors are within the specs. So the other 800,000 transistors is being thrown out to the bin. Okay, so that is not good, right? So that's all I have for today, unless you have other questions. So if no question, I would like to do this activity. So in this activity, what I want you to do is first you choose your partner, and in each breakout room, I will assign one process. Okay, so it can be oxidation process, doping, patterning, deposition, and removal process. Right. So what I want you to do with your partner or partners, okay, is to discuss what is the purpose of the given process. Okay, you should be able to explain and demonstrate. And then what parameter that it could affect, okay, and what could happen to the parameter if the process goes wrong, how it can go wrong, or how you can derive it from any equation.